In the last video, we defined what projectile motion was and looked at some of the characteristics of projectile motion. In this video, we will analyze and quantify projectile motion in more detail using an example. Consider a cannon shooting out of a shell at an angle of 50 degrees with respect to the horizontal ground. The shell is given an initial speed of 15 meters per second. From this initial condition, we can determine information such as what was the maximum height that the shell reached, how long the shell was in the air or the total time of motion, and how far did it travel or its range. Let's start with the maximum height. We'll start by defining a coordinate system using x for the horizontal direction and y for the vertical direction. The origin will be where the shell is fired from the base of the cannon. We will define the upward direction as positive and downwards as negative. The maximum height will occur halfway along the path of the motion. We will designate this height as delta y. So let's begin by looking at the initial state of the shell. The shell is fired with an initial speed of 15 meters per second at an angle of 50 degrees. We can resolve the initial velocity along the x direction as vxo and along the y direction as vyo to represent the initial velocity components along the horizontal and vertical directions respectively. So what is the horizontal component of the initial velocity equal to? And what is the vertical component of the velocity equal to? The horizontal component of the initial velocity is found by taking the cosine of the initial velocity to give us 9.64 meters per second. And the vertical component of the initial velocity is found by taking the sine of the initial velocity to give us 11.5 meters per second. When the shell is launched and it flies through the air, we know that the vertical component of the velocity reduces and it slows down as it goes higher up into the air until the vertical velocity reduces to zero. This is due to gravity pulling it down at a rate of 9.8 meters per second squared. This is when it reaches its maximum height. At this point, the only component of the velocity still left is that of the horizontal component. We can make use of the fact that Vy is 0 at the maximum height. Let's now treat the vertical and horizontal motions separately, starting with the vertical direction because we have more information about it. In the vertical direction, it looks as if the projectile has flown straight up to its maximum height, then falling straight back down again under the influence of gravity. So let's now apply what we know in the vertical direction to our kinematic formulas to try to determine the maximum height. Along the vertical, we know the initial velocity and the acceleration. If we take only the first half of the motion, then the final velocity in that first half is the velocity at the maximum height, which is 0. So we can use the fourth equation, which is v squared is equal to v naught squared plus 2ax. But since we are dealing with the vertical direction, we will relabel the equation using y instead of x. So our equation becomes vy squared is equal to vy naught squared plus 2gy. We can rearrange this equation to solve for the vertical displacement being equal to vy squared minus vy naught squared divided by 2g. Now we can plug in our numbers into the equation to solve for the maximum height. Notice that because we've defined the upward direction as positive, then g is negative because the acceleration vector points downwards. This gives us an answer of 6.7 meters. Notice that the answer is positive, indicating that the maximum height is above the origin in the positive y direction, as we would expect. So while the maximum height is 6.7 meters, what is the total displacement of the projectile in the vertical direction? The total displacement of the projectile in the y direction throughout the entire motion is 0 because the projectile falls down again from its maximum height to its original position. So the difference between the start position and the final position of the entire motion is 0. The total distance traveled though is twice the maximum height, or 13 meters, because the projectile covers a distance of 6.7 meters going up and 6.7 meters going down. We can also use the information available in the vertical direction to find the time of motion. Again, Let's look at the first half of the motion where we know the initial velocity, the final velocity at the maximum height, the displacement, and the acceleration. To find the time taken to go from the start point to the maximum height, we can use either equation 1, 2, or 3 because we have all the information we need to use each equation. Let's use equation 1. Now let's rewrite this equation for the vertical direction. Notice that time does not have a vertical or horizontal component. This is because time is a scalar and not a vector. Time does not have a direction. The time of flight is the same in both the horizontal as well as the vertical direction. As we're solving for time, let's transpose the equation for time, which gives us t being equal to Vy minus Vy naught divided by g. Plugging in our values into the equation gives us a time of 1.2 seconds. Notice that the time has a positive answer. It'll be a worry if time was negative. So the time taken for the projectile to reach its maximum height is 1.2 seconds, which means that the total time of the motion is 2.4 seconds, as it takes a further 1.2 seconds to fall back down again. Now that we know the total time of motion, we can apply this to the horizontal direction to calculate the range. The range is the total displacement of the projectile along the horizontal direction. So far, what we know about the horizontal direction is the horizontal component of the initial velocity being 9.64 meters per second directed to the right. Let's define this direction as a positive x direction. Gravity only acts in the vertical direction, so there's no acceleration due to gravity along the horizontal. And since we're neglecting air resistance, then there's no acceleration along the horizontal at all, which means the velocity along this direction is constant. So now let's apply this information to one of our equations of motion that has time and displacement in it. These are equations 2 and 3. Since the acceleration is 0, so the initial and final velocities are the same, both equations reduce to the following. Relabeling this equation to the horizontal direction gives us the displacement in the x direction being equal to the initial velocity in the x direction multiplied by the total time of motion. Putting in the values for these parameters gives us 23 meters. So by separating the horizontal and vertical components and analyzing them as one-dimensional motion in each of the directions, we are able to solve for various factors such as maximum height, time of flight, and range. We can also determine other parameters such as the instantaneous velocity and position at any point in time using the same method of analysis. The Canon animation in this video was made available from the PhET Interactive Animations project at the University of Colorado. You can open the animation by clicking on the animation link in this module within Video Collaborate. I would encourage you to play with the animations to be more familiar with the concepts explored here. Play around with different launch speeds and different launch angles, as well as changing the height of the cannon. Be sure to turn off the cannon air resistance while exploring the animation though.